If only that was what we were asked for. But remember, what we were asked for was V naught. So our last step is to solve, given what V sub C is, solve for what we're asked to find. So here's our V sub C, once mysterious, now completely understood. We're drawing this circuit for time greater than 0. And we want to find our output. And this is 6 volts in this region. Hey, since we know what VC is, it's a voltage, and we know what that voltage is. A trick that we've used previously is to not draw it as a capacitor. Well, all right, there's a couple of ways we can do that. One way is we could not draw it as a capacitor. We could draw it as a voltage source. And if we draw it as a voltage source, could we find V naught there in that way? Don't write this down, but if we drew it like this, we know what VC is. This is just a thought experiment. We want to find this voltage, V out. Does that, can you tell me how, looking at that, you'd find V out? I know that this, go on.
Could you utilize the rules, one of the rules that we first established with op amps?
Yeah, well, yes, you could. So if this is 6 volts, you know that this is 6 volts. What else could you tell? Well, then you'd know what this voltage is, right? This would be equal to 6. This, the way that the signs are defined, it's saying that the left side is higher than the input. So this would be 6 plus V sub C. We don't know what V naught is, though, because there's could be current flowing through this resistor, and we don't know what it is. Or do we? Do you see how you could tell what that current is? We said this is R sub A.
Yeah, wouldn't it be 0? The current.
Why would the current? Why would this current? We'll call this I sub A. Why would that be 0? You've got a voltage up here that's 6 plus VC. You've got a voltage down here that's ground. There's a voltage across the resistor. Why would the current through it be 0?
It wouldn't.
It wouldn't, but what would it be?
It would be that voltage times the resistor.
Yeah, divided by the resistor.
Or divided by the resistor.
And that's almost true, except the fact that how much would, if this is a positive voltage up here, would it go towards the more positive voltage?
No.
No, the rule says that if you know the voltage, if you know that voltage, then Ohm's law says the current's got to go down. So we just have to put a minus side in front of it. We have to say it's equal to the VC plus, I'm going to do it in the exact same direction so it's clearer. 6 plus VC over R sub A. And that's what I sub A is equal to. So that's one way to do it. And now that we know what I sub A is, hey, watch this. Now we can figure out a whole bunch of things. Now we can say how much current flows through this. All of it. It's got nowhere else to go. If IA goes up here, I has to go through here. How much current goes into the op amp?
No current goes into
None.
the op amp.
So therefore, all of that current has to go through here. So how much does this resistor bump up our voltage is going to start out more positive. It's going to end up more negative. This current has to be the same as this current. So I'm going to call this is also I sub A. But now I can determine what this voltage is. It's equal to I sub A times R sub F by Ohm's law. So I could say my V sub F, the voltage across that resistor, is equal to I sub A times R sub F by Ohm's law. And that's really close to V out. Now I could do a KVL around my green loop. And when I do that, I get, let's start from down here, I get -6. Let's see, going across these inputs has to give me 0, plus my V sub F, plus my V sub naught equals 0. And now I found my V sub naught. I just need to start back solving. V sub naught is equal to 6 minus V sub F. That's equal to 6 minus I sub A R sub F. My I sub A, I found out all the way over here, is equal to minus 6 plus VC all over R sub A, and that's multiplied by R sub F. So this gives me 6 plus RF over RA times 6 plus my V sub C. And what did we say our V sub C was from up on top? This complicated thing. You could probably figure that out directly. It's RF over RA. RF is 80 over RA is 20, so that gives us 4. And 6 plus all that, well, that's adding 6 just cancels this part out. So that would just be equal to 3 e to the minus 10t. And so the whole answer is 6 plus 12 e to the minus 10t volts. Oof. Let's try a different way to find the exact same answer. We want to find V sub naught. So I'm going to spool us back in time to problem 5 because this is hard, right? Maybe there's a faster way, a simpler way to find it. We want to find V sub naught. Is there an easier way to find what this current is? Because if we could find this current, I'm going to call it I sub C. It would be so easy then to say, well, all of that has to be RF. Is there another way to find I sub C? Think about what the rule is for a capacitor. It's equal to C dV dt.
Yeah, we could just divide by C and then take the integral.
Well, but you don't want to. If you wanted to, no.
I'm sorry. If you're looking for I, yeah,
you're looking for I. We found
yeah.
VC in step 4.
Right.
So it's even easier. We just simply multiply by whatever C is. I've forgotten. Is it 5 micros? 5 micros. And let's just take the derivative of this. When we take the derivative of V sub C, the constant goes to 0, and the rest becomes minus 30 e to the minus 10t, and that would be in amps. So let's see, that would be minus 150 micros e to the minus 10t amps. I guess most people would probably write that minus 150 e to the minus 10t microamps. That would be a more natural way to write it. Okay, so that's a part solution. Now that we found that, we could look at this circuit again and say, we know what IC is. All of that current has to go through RF. It can't go anywhere else. And so if we want to use Ohm's law to define a voltage across RF, it has to come in more positive, exit more negative. I'll call that V sub F. So now V sub F, we know, is equal to RF times IC, which from up on top is equal to, RF is 80K times minus 150 e to the minus 10t micros. What's 8 times 150? 1,200, I think. Is that right? Yeah, 1,200. What is e to the minus 10t? What's a k times a micro? It's a milli. So that whole thing is equal to 1. That's supposed to be a milli. So that whole thing is equal to 1.2 e to the minus 10t amps, volts. I just want to check to make sure my feedback resistor is indeed 80K. Yeah. All right. Now that we know what RF is, now we can find our somehow I've done, oh, no, it's equal to 12,000. Which makes this 12. And now we can finally find out what our V naught is. Our V naught, if we do our loop around here, our green loop, we can find it's equal to, so we want to find our V naught here. It's equal to minus 6 plus 0 plus VF plus V naught equals 0. So that's our green loop to the right. That's minus 6 plus 12 e to the minus 10t equals, whoops, plus V naught equals 0. And that gives us V naught is equal to 6 minus 12t e to the minus 10t volts. And somewhere here I've made a sign error here. This should be a plus.
Wouldn't your VF be negative 12 e to the negative 10t because you're multiplying it by 80k times negative 150?
Oh, that was it. Thank you so much. So fixing that, that should be minus, that should be minus. That should be minus, and so that should be plus. Thank you. All right. And so that's the same one we got before, doing it the other way. Any questions about that? That was a lot of algebra. Cool. All right. Guys. Yeah.
The only question that I have, sir, is this either or analysis that leads to the solution, is that
Yes.
circuit like based? So your own, you have to kind of analyze, go through either step based off of your own intuition, or is one better than the other all the time?
I think your question is, I think I hear two questions. The first question is all the stuff that we did in step 5 just EE122 applied. And then is the second thing, as opposed to EE223, is it all just circuits 1? And then the second thing is it smarter to, in general, replace a unknown, replace your voltage across the capacitor with an equivalent voltage source once you know what that voltage source is? Or is it better in general to use the constitutive relationship for a capacitor and then use circuit analysis methods? If those are your questions, the first question, yes, this is everything in step 5, with the exception of just this one step, is all just circuits 1 stuff. And then the answer to your second question, it's not really clear to me. No, there's no general best approach for this. Just try one and see if it works out well for you.
Thank you, sir.
Mm-hmm. Anything else? All right. You've got your collaborative problems. Give these a try. Remember, the hardest part with solving these problems is this step right here, finding tau and replacing your capacitor with a source and with a test current. And I think the second part that's probably hardest is that last step. Once you know what that voltage across the capacitor is, figure out whatever you're asked to find, in this case, the output voltage.